Pluto is a far-off and secretive, small planet that was once a part of our nearby planetary system. However, recent unsettling declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. They suggested that this frigid world is on a potential collision course with Neptune. But how could this truly happen, and what might be the consequences of such a colossal event? Are we witnessing a baffling cosmic anomaly? Or is there something more to this impending celestial dilemma? Join us as we examine the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet, remains a subject of fascination and study in the vast universe. According to recent forecasts by leading experts, Pluto's orbit is alarmingly close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both sounding the alarm about a potential catastrophic collision between these two planets, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. The intrigue doesn't stop there. Pluto's orbit is marked by its particularly eccentric shape, straying widely from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination, which is 17 degrees to the ecliptic plane. The path Pluto follows is significantly more complex compared to other planets. This inclination and eccentricity add layers of complexity to its orbital arrangement. Perhaps one of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For about 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying what we might expect from their positions in the planetary system. This leads to the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers attempted to understand its unique path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out with its steep inclination and erratic shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit, despite these complexities, is evidence of the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects, such as Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they started and how they pull on each other. In Pluto's case, this problem demonstrates how its orbit, Neptune's orbit, and the Sun's gravity all interact in a complex manner. The terms non-synchronous libration, orbital precession, and VZK wobbling are key to this puzzle, as explained by astrophysicists. What keeps all planets in their orbits is non-synchronous libration. For Pluto and Neptune, this term essentially means that when Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from intersecting. Orbital precession, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is situated far above their orbital plane, adding an extra layer of protection from potential collisions. Another key factor in this scenario is the VZK wobbling, named after three scientists, Vladislav, Zeldovich, and Kai, who studied how objects move in space. It involves how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling affects how they move. In Pluto's case, the VZK wobbling helps us understand why its orbit near the Sun is so unusual. Despite Pluto's orbit appearing chaotic, this wobbling helps keep it moving smoothly over extended periods. The VZK wobbling shows that, although things in space may seem wild and unpredictable, patterns and rules maintain some control. These forces help keep Pluto's orbit stable, ensuring that it doesn't collide with Neptune or drift off course. This three-body problem is crucial in understanding how these orbits change due to the way space objects pull on each other. Studying this helps us learn more about Pluto, our solar system, and even distant universes and their stars. Mathematical simulations in the late 1980s revealed that, Despite the stabilizing properties, Pluto's orbit is, in fact, irregular. Minor deviations in initial conditions can lead to massive differences over centuries. However, these characteristics of Pluto's orbit have been found to maintain stability over incredibly long timescales. Monitoring the disturbances from later automated assessments has helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. However, Neptune isn't the only force at work. Jupiter's gravity also plays a massive role in stabilizing Pluto's orbit. Saturn, too, contributes. These studies show that Jupiter's immense gravity is strong enough to ensure Pluto stays on a consistent path for a long time, possibly even for millennia. So, perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely through space without running into trouble. These phenomena are essential to maintaining order in space. Without these mechanisms, the solar system as we know it would be a much more chaotic place. Bodies like Pluto could collide with others or be ejected from their stable orbits, triggering a chain reaction with other celestial bodies. For Pluto, especially with discussions about it potentially colliding with Neptune in the future, understanding its orbit is crucial. This provides a clearer picture of the dynamic nature of the nearby planetary system. The case of Pluto shows how even the most seemingly unstable orbits can reach a state of equilibrium through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and analysis of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the strange nature of celestial bodies, and Pluto's orbit is a prime example of this anomaly. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in Pluto's case. This means that even slight changes in the dwarf planet's position or speed can drastically alter its long-term orbit. Using automated simulations has been immensely helpful for scientists in figuring out how Pluto moves in space. These simulations use complex mathematics to show how Pluto and other space objects, like Neptune, pull on each other. By tweaking small details in the simulations, space experts can see how even tiny changes can make a huge difference in where Pluto ends up. In the late 1980s, these simulations revealed something intriguing about Pluto's orbit. Despite having features like asynchronous libration and orbital precession to keep it stable, its orbit can still be inconsistent and strange. If you start with just a slight difference in where Pluto is or how fast it's moving, its orbit could end up looking completely different after just a few years. Yet, despite this chaos, Pluto's orbit remains stable over massive timescales, like billions of years. This means that Pluto's journey around the Sun has a sort of order to it, even though it appears wild at first. Predicting celestial movements, especially when they involve irregular orbits like Pluto's, is a massive challenge. The inherent unpredictability of these systems means that long-term predictions are often fraught with uncertainties. While mathematical models provide excellent tools for understanding and predicting the future movements of celestial bodies, they also highlight the limitations of our predictive capabilities. These models heavily rely on the accuracy of initial conditions, and any small error or distortion can lead to vastly different outcomes, making precise predictions a daunting task. Beyond the chaotic nature of planetary orbits, Pluto reminds us of the ever-changing and dynamic nature of the universe. While we've made tremendous strides in understanding space, Pluto's case reminds us of how much our knowledge of the universe still remains limited. Grasping the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can significantly affect the stability and trajectory of other bodies within the system. So why are leading astrophysicists recently raising concerns about a potential collision between Pluto and Neptune? Despite all these complex forces working to prevent such an event from occurring, Neil deGrasse Tyson, a prominent astrophysicist and a major figure in advancing cosmology, offers a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, offers insightful analysis on the evolving nature of celestial mechanics and the public's interest in the overlooked corners of space. Tyson's stance on Pluto's reclassification is based on the ever-expanding knowledge of our solar system. He sees the reclassification not as a diminishment but as a necessary adjustment to our growing understanding of the diverse bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He views the complexities of orbits like Pluto's as a reminder of how much there is still to discover in space. The fascination with these questions keeps the study of space so exciting. However, despite Tyson's optimism, his thoughts on Pluto's potential collision with Neptune paint a different picture. His concerns about the fate of Pluto's orbit suggest that we may still have some mysteries to uncover. Will Pluto collide with Neptune? Or is this just another moment of confusion in the ever-changing universe of space? Only time and further research will tell. For now, we are left with a deeper curiosity about how little we still know about our own solar system. We continue to study these celestial phenomena with the goal of uncovering more of the secrets that lie beyond. The possibility of a Pluto-Neptune collision raises yet another question about the mysterious and captivating universe in which we exist. The potential for a collision between Pluto and Neptune raises intriguing issues about the dynamics of the solar system, as it challenges our traditional understanding of planetary stability. That two celestial bodies with such vastly different properties could collide is both unsettling and fascinating, especially considering the current relative stability of their orbits. Given that Pluto is located in the outer reaches of the solar system, far from the major planets, and Neptune is itself a gas giant with a strong gravitational field, the implications of such a collision would be immense for how we understand gravitational interactions and the evolution of the solar system. To understand the dynamics of a potential impact, one must first consider the structure and properties of the two planets. Pluto, despite being a dwarf planet, contains various elements and compounds believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere made mostly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a giant gas planet, is composed mostly of hydrogen, helium, and other lighter elements, with a deep, dense atmosphere. A collision between such disparate bodies would profoundly affect their structure and behavior, potentially creating an event that would be observable across vast cosmic distances. What makes this hypothetical collision particularly intriguing is the influence of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in keeping Pluto's orbit stable, it is not the only factor at play. The presence of Jupiter, the largest planet in the solar system, is another crucial factor. Jupiter's massive size, strong gravitational field, and gravitational influence provide a stabilizing effect on Pluto's orbit, preventing it from straying too far into Neptune's domain. Additionally, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making it unlikely that a catastrophic event will occur between Pluto and Neptune. However, despite the apparent safeguards, ongoing research has also shown that the relationship between Pluto and Neptune is not as simple as a straightforward collision course. The gravitational resonance between the two planets, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a sort of celestial lock that prevents them from coming into direct contact. This resonance is a key reason why Pluto and Neptune's orbits, while intersecting in the vast expanse of space, have never resulted in a collision. This gravitational resonance is one of the most fascinating examples of celestial mechanics in the solar system. It serves as a reminder of the intricate and delicate dance that governs the motion of celestial bodies. While the resonance ensures that Pluto and Neptune never occupy the same region of space at the same time,